My name is Ali and I will be doing the video problem. This is a problem. Its specifications are highlighted. So in order to find the surface area in one of the regions, we'd have to do 1/4 multiplied by the surface area of a sphere. It would leave us with pi r squared, which is equivalent for both regions. The boundary conditions, we know that the electric fields are tangential, so the electric field will be the same for both conductivity regions here. So electric field is the same in both regions. So now we need to find electric field. We can do that by equating the currents. We know that the currents going in region 1 and region 2 summed up is the total current. And we know that current density multiplied by surface area is equal to current, and that current density is equal to electric field multiplied by conductivity. Subbing that in, we're left with this equation for electric field, where S is pi r squared. So once we plug that into our voltage integral, we are left with this equation. Now we got this by just solving the integral. We moved out all the stuff that wasn't being integrated. We integrated 1/r squared, and the 1/infinity was 0, so we got rid of it. And now that we have our equation or expression for V, all we have to do is divide it by I, as shown here, to find resistance. And we did that here. So once you plug in the values for resistance, then the resistance is 31.831 ohms. The second half of this question asks for the power loss in each of the regions. So that can be found by getting the power loss equation, which is on the formula sheet right here. And note that dV for a sphere is right here. So we get that from the formula sheet. But this 1/4 value is something that I added because each region is not a full sphere. It's 1/4 of that sphere. So we take out the constants and we solve the integral. A neat thing is that the integral here on R is the same integral that it was in the previous question, so that saves a bit of work. And the 1/infinity becomes 0. And we can cancel out the numerator and denominator like terms. And it leaves us with this expression for power loss in region 1. And the power loss in region 2 will be exactly the same, except its conductivity is going to be the conductivity of region 2. Now this makes sense because this equation is identical for region 2. The only difference would be this, the conductivity. The geometry of the two regions is the exact same, so that's why we can use this equation. And we didn't have to solve the entire integral again. So now that we have the two equations, we sub in our values and we are left with 15,915 watts for region 1 and 63,661 watts for region 2. So you add those together, it gives you the total power, which is going to be around 80 kilowatts. Thank you for listening, and I hope it was helpful.